Okay, let's start. Today we will talk about state and finite state machines. So the state and finite state machines, FSAM, are the key components in the controller. So we have the combinational logic, like the AND, OR, NOT gates. More complex combinational logic, adder and multiplier. And then we have memory elements like the latch, flip-flops, JK flip-flop, SR flip-flop, different types of flip-flops. By combinational logic and memory components, we can actually implement some circuits with the clock, because we can temporarily store some intermediate values or states. Next, we will cover the points of how to build a controller. So we need a controller to control our circuit with the clocks. For example, the first clock, you need to do this. In the second clock, you need to do that. So that's the reason why we need a state. For the combinational logic, we do not have any states. We do not have any states. When you apply your input, you can get your output immediately. So nothing computed in the present in this cycle can depend on what happened in the previous cycle or in the past. So we need a method to build a stateful circuit. And we need, of course, we have the latch to record the data. We have the flip-flop which can record data. And we also need a state holding devices. And we need a finite state machine. We can have a different method to store one bit. Latch, flip-flop, different latches, different flip-flops. We can also have the decoder and the encoder to index those memory elements. For example, I have one array of D latches. I can organize them in some columns and rows, and then I can use my decoder and encoder to decode. I want to access the third row of this latch array. And then we need a finite state machine to control the circuit. So in this lecture, we will cover two types of finite state machine. One is a so-called mini machine. The other one is a so-called Moore machine. The clock can help coordinate the state change, can trigger the state change, often generated by some dedicated clock timing devices. For example, your CPU is a 1 gigahertz, can run at a 1 gigahertz frequency, which means that one period on your CPU, one clock is 1 nanosecond. And then the frequency can reach 1 GHz. So this is one example of your clock. You have a clock can be high, can be low, and you have a rising edge. You have falling edge. Based on the memory element you used in your circuit, latch or flip-flop, the state change can trigger by different part of the clock. Some of them can trigger by the level, clock level, low or high. The other may trigger by the rising edge and the falling edge. So this is one clock period, you have a half cycle as the high, half cycle as the low. This is clock high, this is clock low. This is a falling edge. This is a rising edge. If you use a lot of latch, then it's a level sensitive. For example, the D latch. Some change can be triggered by the level clock high. When the clock is low, everything is hold. The other types of circuit can be managed by the edge, edge trigger, because you use a lot of flip-flops. You can use a falling edge to trigger everything. This is a negative edge trigger, or rising edge trigger anything. This is a positive edge trigger. One example is the memory element itself. This is a D latch. The input is a D, of course, and the clock. The output is a Q. So when the clock is a low, when the clock is a low, there is a hold state. The output will not change with the input. Q will not change with the input. But when the clock is high, like this part, if there are some change on the input, the output will change immediately with the output. If we have a two D latch connect sequentially, then we have a D flip-flop. Then this component can be triggered by the rising edge. You can check the details back to the working mechanism of the D flip-flops. When the clock is low, these two clocks are complemented. One is a clock bar, the other is a clock itself. So when the clock is low, the clock bar is high. So this is a transparent D latch. This high signal will reach here, will reach this part. But this is a hold state. This high cannot pass through this D latch to reach here. Eventually, the output here is still low. However, when the clock is changed at the rising edge, this one is hold. So you can always have the high signal here because the first D latch is hold. The second one is a load, is transparent. The output here will change with the input. The input is high. Then you have a high here. You can see that the output change is triggered by this rising edge, by this one. The output change from low to high. So we can use these, the characteristic of these memory component to build a circuit which can use different clock to do different tasks. For example, when the clock is low, it can do computation. When the clock is high, it can save the intermediate results and hold it. And when the clock goes down in the second cycle, it will do the compute again and then save the intermediate results, so on and so forth. So this is a negative edge trigger. So we use the falling edge to synchronize the computation and the saving. So in this way, we can do different tasks. For example, we can compute A in the first cycle and then save the results in some latch. Or here, in this case, it's a flip-flop. Save some results in the flip-flop. And then in the second cycle, I can compute B. Maybe compute A is addition, compute B is a subtraction. Something like that. This type of circuit can also be controlled by the rising edge. It's a positive edge figure. So in this case, in order to manage which cycle to do what, we need a finite state machine. We need some internal state. For example, only after I compute A and only after I compute A and compute B, I can do the computation on C. Maybe you have some, graph like this. So in this way, you definitely need a finite state machine because you need some internal states for your circuits, in your circuits. So when your circuit finished computing on A, it reached the first state. If it do not compute the B, then it will never reach the second state. But if it did compute B, then it can reach the second state, so on and so forth. So the output and the next state definitely depend on the input and the current state. You cannot directly compute the C by skipping the computation on B. So the finite state machine can be summarized like this. You have a list of a set of finite set of the states and a finite set of the inputs. You have the states, inputs, and output, and the state transmission functions. The next state depends on the present input and the present state. So we have a state, input, output, and the transitions. The transition means from a state A to state B, from state B maybe to state Z. So a finite state machine can be implemented by automata model. This is one example. So in this example, you have a current state. You have input. And then you have output. And you have the next state. This is a register. You can call it a flip-flop to temporarily store the next state. When you store the next state in this buffer, in the next cycle, the next state will change to current state. It will feed this current state input to this combinational logic, and then you can change your input here. So the simplest example of this automata is an accumulator. You do an addition here, and then you can send out your output. And then you can temporarily store your intermediate results in the registers. And the next cycle, you can change another input and accumulate that input into that accumulated results. The input are from external world. You can change that every cycle. The output can go back to the external world, but you have internal states, current states, next state, and the state after the next state. And then you have a combinational logic here. So this is a finite state machine example. The input can be up and down. The output can be on and off. So we have 4 states, which are A, B, C, D. And then the connection here are the transmission. We have a specialized state, which tagged like this. Besides the state symbol itself, we have one extra circle here. This is the start state. You can start from here. And the output depend on the current state, which is A, and the input. And when you have a input, you can get a output and you can transmit to another state. We can actually encode this up and down, on and off by some binary signals here. And then we can encode the ABCD by 2 bits, which are 0, 0, 0, 1, 1, 1, and 1, 0. And the on and off are 1 and 0. Up and down are 0 and 1. And then we can change the entire state, entire finite state machine like this. We can encode the entire finite state machine like this. This part, of course, is the input, and the right part is the output. And then you still have a lot of transition here. So we have 2 types of finite state machine. The first one is a so-called Morse state machine. The output depends on the current state only. It does not depend on the input. For the Mealy machine, the output depends on the current state and the input. The Ant brain is a Moore machine. Output does not react immediately to the input change. We could have specified a Mealy machine. So in the previous slides, we have a Mealy machine because the output depends on the input and the current state. As the input change, so does next state doesn't commit until the clock event. So we can write the Mealy machine like this. This figure is exactly the same as the figure I introduced where I introduced the finite state machine. So this is a Mealy machine. You can see that the output depends on the current state and the input in this figure, because you can find this symbol here. So the output and the next state depend on both the current state and the input. This is the Mealy machine, which is also the previous example I used to introduce the finite state machine. The output here depends on the current state, both the current state and the input. So if I change the input from up to down, then you'll go to another transition and you will have another output. So the output and the next state depend on both the current state and the input. So this is the Moore machine. For the Moore machine, the output here only decided, the output here only decided by the current state. But the current state and the input decides the next state. The difference between the Moore state machine and the Mealy state machine is that in Moore state machine, the output depends on only the current state. But the Mealy machine, the output depends on current state and the input. So if we use the Moore machine to build the same finite state machine, where we have input up and down, output on and off. And then we have 4 states, A, B, C, D. This is the new Moore finite state machine. So in Moore finite state machine, we combine the state with the output. Here we have A and off. It's possible for us to have A and on. And then we have a B on, D off, C off. And then we can have also the, the transition here. But the transition is only enabled by the input here. So the mini machine tend to have a less state, different output, may share the same state. More states are safer to use because the output change at the clock edge always 1 cycle later. In mini machine, input change can cause output change as soon as the logic is done. A big problem when 2 machines are interconnected, we will have some asynchronous feedback problem. The mini machine reacts faster to the input. It will respond in the same cycle. You don't need to wait for 1 extra cycle. In Moore machine, more logic may be required to decode the state into the output, which means that you can have a more gate delay. So these are the 2 figures for the mini machine and the Moore machine. So in order to overcome that asynchronous feedback problem, we can have some registered Moore machine. Or we can call it a synchronized, registered mini machine. Or we can call it a synchronized mini machine. We registered input, both the input and the output here. So there is no glitch on the output. So it's easy to implement in programmable logic. So it's equivalent to a Moore machine without the output decoding. The output can be computed on the transition to the next cycle, the next state. We can view the output as an extended state vector. And then I will give you an example to further explain the difference between the mini machine and Moore machine. So this is a finite state machine. The left on the edge is the input. Here, the right part is the output, and then we have A, B, C, 3 states. The start state is A. By a reset input, we can reach that A. So in this case, we have a reset control signal. When the reset is 1, no matter what's the input and what's the state, you have to go back to the A anyway. So here the next state is A, and the output here is a 0. So I'm just writing this finite state machine back to a truth table. So when the reset is 1, then no matter what's the input and what's the state, you have to go back to the A. And the output here is a 0. So when you are at A, when the current state is A, assume all the input here are reset is a 0. Assume the input here is a 0. then you will go to B. The output here is a 0. When the input is a 1, then you will go to C. The output here is a 0. So you can, convert this finite state machine to this table. So let me ask this question. So what's the type of this finite? What's the type of this finite machine? The answer is mini machine. Why? Because the next state is dependent on the input and the current state. On each edge, you have a input, and then you have the current state. You can also have an equivalent finite state machine as the Moore machine. So now the output is incorporated into the state. So each state has an output. So remember, in the previous mini machine, we have only 3 states. But in the equivalent Moore machine, we have 5 states. Some of the states are developed from the A, B, C. But they may have a different output. For example, in the previous example, in this example, it's possible for B to output a 0. It is also possible for B to output a 1. So B has to be divided into 2 states in the equivalent Moore machine. B can be divided into the B output 0 and D output 1. And then you can also rewrite this finite state machine to a truth table like this. Now the output is only decided by your current state. Because in one state, you can only output 0 or 1. And then we will use one real example to design a finite state machine. This real example is how to design a wandering machine. So we can have 3 types of input. We have 2 types of input. One is a nickel, the other is a dime. We can have 3 nickels, 1 dime, and 1 nickel, 1 nickel, 1 dime, or 2 dimes. The input is N, D, and reset. We always have the reset signal here. When you have the reset, you have to go back to the initial state, the start state. The N indicate nickel, D indicate dime. The output, whether you open the, whether you send out the drink or not. We can assume that N and D can hold for 1 cycle. And each state has a self loop for N equals to D, D equals to 0. So there's no coin. And then we can draw a state machine like this. If we have the reset, we always go back to the S0. At S0, we can input N or D, and then we go to different states. And then eventually we can have open or not open the machine. And this example is the finite state machine example with the truth table. In this example, we have 4 states. And because the state has a input, only this one is open. All the other states here are closed. So this machine is actually a Moore machine. And then you can have 2 types of inputs. You can encode these inputs into binary representations, 0 and 1. And then you can reach the next states. The next state, of course, has a state. For example, for 0 cent, it's always a 0, which means it's closed. Only the last one has a 1. So this is a Moore machine. And then this is the truth table. We can reuse our K-map technique and simplify that truth table by K-map. And eventually we can design a combinational circuit like this to control that finite state machine. And then we can have an equivalent Mealy machine like this. During the finite state machine design, we can use one-hot encoding. We can encode N state using N flip-flops. And we assign a single 1 for each state. For example, this is the 4th state. This is the 3rd state, the 2nd state, the 1st state. And we can propagate a single 1 from one flip-flop to the next. And all the other flip-flop output are 0. We can draw finite state machine directly from the state diagram. Each state function need 1 denser state bits as input, 1 product term per income edge. The disadvantage is, of course, we have a complex state diagram. This means a complex design. We will have a larger hardware overhead. We will consume more gates. And the larger machine, of course, require more flip-flops because you have more states. And in this case, it's possible to decouple or decompose the entire design into small pieces. That can also be implemented by one-hot encoding design. So either we have a N plus M states for 2 machines, or we can have a N multiply M states for 1. Apparently, in this case, we prefer the first design because we will have a less states. So this is the example of one-hot encoding. Now we also encode the state by binary like this. Because we only have 4 states, so we only have 4 bits for the one-hot design. And in this case, we can rewrite the entire Boolean algebra for this machine like this. Of course, this is based on the simplification results. achieved by your K-map. Any questions? If no question, we can stop today. Thank you very much.